Okay, so let's discuss the next and the very important concept of the distributed system or the system design, that is resiliency. So with resiliency, we mean that the system should be able to withstand the failures and should also able to recover from that failure without the human intervention. So that a design or creation is known as resiliency engineering. Okay, so let's discuss that and how do we implement that. So we'll be using a pattern called as circuit breaker pattern. So let's discuss how this pattern works or how it is implemented. So basically, in a system, in a distributed system, a failure is a guarantee. But the only difference here lies is how we handle that failure. Whether that failure gets into a minor glitch or it completely brings down the whole system. So that's where the engineering difference lies in. Okay. So here with the circuit breaker pattern, we will try to make sure that any failure will lead to a minor glitch and not a breakdown of the complete system. So let's discuss that. So here we'll take an example of order service in an e-commerce application like Amazon and Walmart. So in a normal scenario, when a user places an order, there are multiple services that will be called to process that order. So the first service that will be called is the payment gateway. So as we know, the payment system, the payment gateway is something, an external service which needs to be called by the e-commerce application to get the payments. So once the payment gateway is successful, once the payment is done, then it needs to call the shipping service to update the shipping process. Also, it needs to call the inventory service to update the inventory, right? And at the same time, these other services also calls the order services to get some relevant information. For example, the inventory service may call the order service to tell that there is a restock has been happened, or shipping services may call the order service to get some order related information, right? So these kind of inter-services communication happens, and all of them will be successful only when all the services are up and running, right? So this is a normal scenario. Now let's consider a scenario where the system sees a cascading failures. So for example, let's say it's a Black Friday sale and the number of users trying to shop or place orders starts increasing. Okay, so in this moment, let's say we take an example of the communication between order service and the payment gateway. So let's say the payment gateway was like processing around 10 requests per second in a normal scenario. But due to a very high load on the Black Friday, the number of payments processed by the payment gateway per second starts to slow down. Okay, so from 10, now it's, let's say it starts to process only 5 payments per second. So when this slowness starts, initially at the 0th second, if we take we may not be able to see the impact. Okay, but now as the users grows and as the number of requests grows, there will be a point of time where the number of payments processed by the payment gateway will come down to 0. Okay, so the moment the payments processing comes down to 0 and the number of requests starts to pile up in the order service, the resource starts exhausting. That is, any server will have a limited amount of threads and a RAM. Okay, and every request will consume a thread and certain amount of RAM. So when the request starts to pile up and they are not getting processed, so the number of threads and the RAM completely gets exhausted and the service will become unresponsive. Okay, so this is a point of infection, you can say, right? Where now the order service is unresponsive, it is infected. So now how does that impact the other systems? So this is where this is how the order service comes down, where because the other bank API slows down, so the order service hangs while waiting for the response. So every pending request ties up to a worker thread in the server's pool. So due to that, with thousands of incoming requests, the thread pool will get exhausted and there will be no thread to handle the new request. So that order service becomes unresponsive. Okay, so now here the order service, we can say, is in infected state. Now whatever the services that will try to communicate with that will also gets unresponsive. So for example, now as we discussed initially, let's say the inventory service wants to give an update of the restock to the order service. So in that case, when it makes a request, it will not get the response from the order service. So now that request will also be in a waiting state. So due to that, when such kind of request comes from the inventory service, the inventory service resources will now starts to get exhausted. So now then the inventory service goes down. So similarly, the shipping services, if it tries to communicate with the order service, then the shipping service over the time will get exhausted or its resource gets exhausted and it goes down. So like this, all the other services in the system starts to goes down when we have one service that gets infected because of an external service, that is payment gateway. So this is where we need to implement the circuit breaker pattern, or a system that is resilient, or a system that automatically withstand the failures and comes back. So let's discuss how we can do that. So here we can implement a circuit breaker pattern between the order service and the payment gateway, where the circuit breaker will keep on checking for the failed requests. So this prevents the cascading failures. So engineers implement a circuit breaker proxy between the order service and the payment gateway. Okay. So how does it works? Basically, in the normal scenario, which we call it as a closed state. So during that, there will be a normal request and response between the order service and the payment gateway. So during this state, there will be normal request and response between the both the services without any impact. But let's say when the services or the request starts failing, so at that time, the circuit breaker observes this for a couple of requests, and if it continues after some requests, then the circuit gets into open state. That is, there will be no further requests between the order and the payment gateway. So the order service will fall back into a fallback mechanism, and it will be responding a static response to the users. And then the next states, and that is a state we call it as an open state, when there is no request and response between the order and the payment service. But after some time, the order service will check for one of the requests. So it will make sure that it will just check after some time that whether the payment service is back or it is responding or not. And that one request or that state, we call it as a half open state. That is, we call it as a testing state. So and during the testing state, if the request and response is successful or it is normal, then it will again goes back to the closed state. And but if it still fails, then it will again open back the circuit. Okay. So that's how the whole system or the process will work, and that is how automatically the system will become resilient. Okay, so whatever just now we discussed, I'll just look at that in a more close manner. So here that is a closed state where there is a normal request and response between order service and the payment gateway without any errors. But now as the errors starts, that is failure threshold met, that is example 5 failures in a row, at that time the circuit will goes into open state, and now there will be no direct request and response between the order service and the payment gateway, and it will just returns a fallback response. Okay. Next, there will be half open state, and during that it will check for one of the requests. If it succeeds, then it will close that circuit, and if it still fails, then it will again goes back to the open state. So these are the 3 main states. So what is the strategic value of this implementation? So with this, the system is still resilient and it is still up and running, and here the users are getting a proper response, whether they should wait or whether they should come back after some time. It will not make the user to wait for the response forever. Okay, and this will also make sure the other resources or the servers in the system does not get impacted. Okay, so that's how the whole system become resilient to the failures. So you can also say what is the strategic value, that is a high latency is worse than the downtime. Okay, so with this, without the circuit breaker, the latency of that is the response time gets increases, but with the circuit breaker pattern, the user will immediately get the message that system is busy, save for later or try again after some time. Okay, so that's again another strategic value that we'll get with this implementation. And other strategic value is that, let's say this happens in the midnight or during a 3 a.m. Where when the engineers are not available. So during that time, we don't need an engineer to come back and fix this. So it will automatically goes into open state, and it will keep on checking after some time whether the external service, that is bank or the payment gateway, is back or not. So once it is back, it will automatically goes into closed state without any human intervention. So this is how the system is self-resilient. Okay. So to implement this, there are many modern toolkits available. So if we want to implement this in Java, Spring Boot, microservices, then we have a Resilience 4G option. So that we will look into next. I'll just show you a demo how we can implement this. Then if we are into a .NET architecture, then we can go with Poly. And if you want to implement this resilience in the Kubernetes architecture, then we can go with either Istio or Linkered. With this, we can implement the resiliency in the architecture. So we'll be looking at Resilience 4J in the demo. So in the summary, the principles of resiliency are that it should fail fast. So you should not keep the user waiting forever. Then it should recover automatically and also protect the other systems in the architecture. Okay. So next, let's look at a simple demo of how we can implement the circuit breaker pattern using Resilience 4J in Java Spring Boot microservices. Okay, so let's discuss a quick demo on how do we implement a circuit breaker pattern or a resiliency in a microservices architecture. So for the demo, I have created 2 simple microservices, and here in the microservice 1, I have a simple API that we are calling, and this API is going to further call the another microservice, that is microservice P, and it will just return us a response. And in case of a failure, or when the system, that is microservice 2, is not responding, it will go back into a fallback method. So let me explain you how does this whole flow works. So for that, first of all, I have added a dependency in the pom.xml, that is the resilience 4J dependency, and an actual dependency to get the state health of the application. But the important one is this resilience 4J dependency, and along with that, Spring Starter web dependency has been added to start this application using the Tomcat container. Okay, so now going next, we have in the application.yaml, we need to add these properties. Let me quickly explain you what this property is about. So here, this is where we are configuring the behavior of the circuit breaker. So here, using this, I'm adding a name to this property, like wherever we will be using this service P, that circuit breaker will behave according to this configuration. So the first property we have is sliding window size. So this shows the size or the number of requests this circuit breaker should keep in the context. And the next property we have is minimum number of calls. This denotes the minimum number of calls that needs to happen before the circuit breaker comes into picture. Okay, so that is 4. Now failure rate threshold. So this is a percentage that we are telling that at least if 50% of this in this window, if the request fails, that is two or more, then the circuit breaker should go into open state. Next, we have the wait duration during the open state. So when the circuit goes into open state, it will wait for the next 10 seconds before it will try for a request to the affected service. Okay, so permitted number of calls in the half open state. So the minimum number of calls it will check when it needs to test before going into open closed state, it is 1. Okay, so it will just check for 1 call. If it fails, then it will again go back to the open state. If it succeeds, then it goes back to the closed state. So this state is what we call it as a half open state, where it is testing the affected service and with just 1 call. Okay, so if you make it as 2, then it will test for 2 subsequent calls, and if both of them fails, then it will go back to the open state. So that's the permitted number of calls in the half open state. And then finally, we have automatic transition from open to half open enabled. So we are making sure that the system automatically transits from the open to the half open state. So we are keeping it as true. Okay, so that's an important property that we needed to add, and this is for the actuator property to get the health of the application. So now coming to the controller. So here I have created a REST template so that to make a call to the another service, and we have a controller, and in this controller we have a single API that is going to be called by the client, and this API is further going to call the another microservice. So this is a point where we are making a inter microservice communication, and we may get a failure where if the microservice B is not responding, then the microservice A may get exhausted because it may go on infinite waiting state. So to avoid that situation or scenario, we have implemented the circuit breaker pattern. So here we have implemented a circuit breaker by adding the annotation here, and in this annotation we have added 2 parameters. The first one is name. So this name denotes the property that we have defined in the application.yaml, that is the service B. So these properties will get applied to this function or to this method whenever the circuit goes into open state. And next, we have also defined the fallback method. So we have defined the fallback method name over here. So when the circuit will be in the open state, it is not going to make a further call to the microservice B, but instead it is going to return the response whatever we have added in the fallback method. Okay, and here we need to make sure that the fallback methods method definition matches to the method where we have implemented the circuit breaker. And the fallback have a throwable parameter that is needed because the resilience 4J will pass the whatever the error or the exception to the fallback method, and it needs a parameter to receive that. So that is the reason this is an additional parameter that has to be added over here. But apart from this, everything else that is a method definition should look like the function where the circuit breaker has been implemented. Okay, so now let's look at the another microservice. So in this microservice, we just have a simple API, or there are 2 APIs. That is, the first one is an API that we'll be using to toggle the failure or the normal state of the application. So if you call this API, then initially it will be in a normal state, and if you call it, then it will just turn that into a failure state. So that will help us to demonstrate the circuit breaker pattern. And we have another API that is going to be called by the microservice A. Okay, so that's it. These are the 2 APIs we have in this application, that is microservice B. Now let's look at this demo quickly. So let me run this. Okay, so our application is started, and we have Our microservice A is also up and running. Now let me just make a call, okay, to the microservice A. Okay, so we have made a call, and right now the microservice B is in a normal state. So that's the reason we are getting a response from the microservice B. Okay, so basically we have called this API. We have called this API, and this API has made a call to this API in the microservice B, and finally we are getting this response. So let's make a couple of requests. So to create that window, so it's not important that we need to create, but yeah, just for a normal state. So now we have made a couple of requests, and all of them have been passed. Now let's make another call, and let's put the microservice B into a failure mode. So for that, now if I made a request, and now the failure mode is on. That is, now in this case, if whenever this API is called, now the fail is set to true. So that's the reason it will get into a runtime exception. So that will leads to a failure. So now in this case, what is the behavior we are expecting? So initially, whatever we have properties we have implemented here, that is, it will a window of four requests. So when we start to make a call from the client, so initially for the first two requests or the first three requests will be reaching to the microservice B. But when we make the next fourth request, then the fourth request will not be reaching to this service because the circuit will goes into open state. And post that, when we wait for the next 10 seconds, and if after that, if we make next request, then it will just check for one. If it is in a past or in the normal state, the circuit will goes back to the closed state, else it will still remain in the open state. So let's implement that, do that practically. We'll get it completely. So now, as we know, the microservice B is in the failure mode. So let's make a call, and let's see whether we'll get a request over here or not. Okay, so you can see that we have received it for the first time. So if I just do it again, you can see that again we have received it. Again we have received it. Now if I do it, we'll see that we'll be not receiving it because the circuit is in the open state. So now after 10 seconds, if I try it again, you will see that one request will be there, but post that it will again, it will not be making the subsequent request. It will just make one request after 10 seconds. So now 10 seconds has been passed. If I make it now, you'll see that we got it. But if I again continue it, you will see that we are not getting any further request because it again went back to the open state from the half open state. So that keeps on repeating after every 10 seconds. Okay, so that's how the system become resilient automatically without any human intervention. So now it will automatically goes into closed state as soon as we'll put back the microservice B into a normal mode. Okay, so now if I make a request again, we'll see that we have got one. But if I make it again, you will see that it will not be getting any further requests because in the half open state, we have made sure that we'll be making only one permitted request in the half open state. Okay, so now let me just put back the microservice B into normal mode. So now it is in a normal mode, and now if I make a call, it will automatically get the proper responses. Now it went into a proper closed state. So that's a simple demonstration of how the circuit breaker is implemented and how it works practically. Okay.